good afternoon and welcome back to the final live discussion here on the Nexperia Power Live GaN channel. We're here with you for approximately 45 minutes with some very special guests of ours. As before, please do feel free to contribute by using the speech bubble in the bottom right of your screen. You can contribute questions, thoughts or comments throughout the whole 45-minute period. So before I hand over to our live panel, let's take a small look at what we're about to discuss in this short video.
And so the automotive industry is looking across a range of materials for the next generation battery electric vehicles, including gallium nitride. We have to be 100% sure that there's not going to be any issues with any parts of the next generation battery electric vehicles, including the drive components.
It's great to be working with a company like Nexperia. This is where we can really bring the value from Ricardo in that complete system understanding, taking the requirements that we need to deliver competitive products at a vehicle and propulsion system level, and really showing how to develop and apply the semiconductor GaN technology for the very best benefit in how we develop that into a complete inverter and how that could be applied into a propulsion system.
And part of the project of putting our GaN devices into a module and into an inverter and trialing them by Ricardo is to find those failure modes so we have a clear understanding of how the vehicle can be driven most safely and most reliably. You have to put them in a situation where the vehicle can perform all the things it would normally do, such that we then understand the limits of the GaN devices. This is a real solution that I think a lot of automotive designers will be interested in having a look at.
Super, really nice snapshot of an extremely exciting topic that we're about to delve into. So with that, I would like to hand over to our panel host for today, Dr. Will Drury.
Thank you very much, and what a fantastic opportunity and how exciting it is to be here with you today to talk about gallium nitride and how that's moving forward in the automotive space with some great technology and application stuff. I'm Will Drury. I'm the Challenge Director for Driving the Electric Revolution at UK Research and Innovation, and some of this stuff is right at the forefront of that innovation and innovative area. So I'm really hoping today we're going to get some fantastic questions from you joining us that we can put to our panel. So on our panel today, we've got Michael Le Goff from Nexperia, Simon Ansell from Ricardo, and supporting them we've got Dr. Dilda Chowdhury, who has those that have been with you for the day today, enjoying the GaN experience. Have just seen a fantastic and interesting look at the future with Dilda on the previous show, and also James Hoyle here from Ricardo as well. So hopefully over the course of this, we'll look at the gallium nitride itself, understand a bit more about that and how it can be used, but also the applications it can go into. So without further ado, Michael, do you want to give everyone a little bit of background about yourself, where you come from, what your involvement in this is?
Sure, I'll be light on myself, but thank you, Will. I do recall when I was running another business, making an announcement in June 2001 that together with Group Sagem in France, and this was after 3 years of development, we were to supply IGBT power modules for the new Renault Kangoo, the all-electric minivan. And now almost 20 years later, and plenty of scars, we as consumers appear to be ready to adapt to fully electric vehicles. The pundits are even reporting the all-electric vehicle as a truly emerging market. And there are a number of factors behind that, which I won't go into. But for Nexperia, the journey to develop a high-efficiency, high-power switch ideally suited for the electric vehicle began in 2012. So again, difficult to continue to use the word new, but that's just where we are. The challenge for our business at Nexperia in this process of introducing what is considered new products based on new GaN technology into new applications that are being challenged in new end markets regardless of how long we've been working on the solution, is one of confidence. And when we talk to the global automotive tier ones and OEMs who are faced with this challenge of ensuring that that means you and I, will make the decision that our next vehicle will be fully electric, they need to have the confidence that the switch, the basic part of the vehicle, works well and is going to be reliable. This market demand shift means moving from less than about 2% of total vehicles today to nearly 30% of vehicle production in 2030, less than 10 years now. And that means about 30 million battery electric vehicles on the road being produced every year by that time. And this is a monumental market/technology shift. Forget smartphones or solid state lighting or flat screen displays and monitors or digital telephony. This shift to battery electric is considered by many to become the single largest technology transition ever by some margin. In an effort to try and eliminate the perceived risks in the fundamental power switch in the electric vehicle, and to provide both the confidence in the GaN technology and the GaN products, we've engaged, the premier automotive design company in the world, Ricardo. And it's been an absolutely pleasure working with Simon and the entire team there. Together, Ricardo and Nexperia, we've developed a working prototype in the first instance of this 50 kVA traction inverter. And that was based on Nexperia's first generation fully qualified GaN technology, and it's in a 2-liter form factor. And we expect to be able to bring this up to 100 kVA and then 150 kVA with our next generations of GaN platforms in the same 2-liter format. And we've learned quite a bit in the process, this designing and working in this particular environment. And we're happy to share and discuss that today. But more importantly, once we get access to testing facilities again, post the existing pandemic crisis, we also expect to be able to share the test results that Ricardo will generate, putting the inverter through all the regimes that a typical electric vehicle will see, but also to continue to stress the inverter to device failure. And that's something we really need to understand and clearly, and that will provide the confidence in both reliability of the switch. So we, collectively, everybody on the call as an industry who are aimed and focused at supplying this next generation technology shift, these electric vehicles to the public, have a lot of learning to do as we ramp. And you're talking about startup production really ramping 2023 and 2024, so not a lot of time. And I do hope and I do expect that the development work that we have done with Ricardo forms part of that overall learning.
Fantastic, Michael. I think what you were saying there, you've got new technology and a new package and a new application. You've made life easy for yourself, haven't you, on this one? So I think the future is certainly exciting and interesting. But thank you very much for that introduction. I think it really gives us a framework under which we can hopefully carry on this dialogue today. So at this point, I'll bring Simon Ansell in from Ricardo. So Simon's a principal engineer at Ricardo. Simon, do you want to give a quick little bit about yourself, Ricardo, and what you've been doing today in this area?
Sure, thanks, Will. So I'm Simon Ansell, principal engineer based in the Cambridge, UK office of Ricardo. Ricardo is a worldwide global automotive design consultancy, although we're now sort of branching out into other areas, including energy, environment, and rail. And we take customers' projects, basically from anything from a proof of concept through to a fully validated product ready for production. As I mentioned, we've got multiple sites across the globe, and we're able to use expertise from any one or multiple sites to deliver these projects. The Nexperia project was primarily run out of the Cambridge office, where we have all necessary skill set to deliver this, right from the very basics through to producing the assembled inverters that we will then put onto our dynamometers in our showroom site on the south coast of the UK. As Michael mentioned, really, there were many new aspects to be covered in this development. So we broke the project down into a series of smaller projects to build on confidence bases throughout, so that we were basically hopefully left with no surprises throughout the development. And really the first the first part of the project was to prove that we could actually parallel GaN devices. Obviously, they've got extremely fast dV by dt turn on, turn off. So current sharing was seen as a foundation stone that we had to set in place to prove that we could get current sharing between parallel devices, and that's where the first part of the project focused. And it was a learning curve. I won't say it wasn't, but it wasn't actually overly difficult, but there were a number of things that we did find throughout the discovery. One was that we needed better test equipment than we had at the start of the project, which wasn't an issue. During the early parts of the current sharing development, we were using a thermal camera to assess the body temperatures of the GaN devices while we were pushing quite large currents through them. And we had the thermal camera set up looking at the devices, and the temperature rise of the devices was barely above background. You know, it was sort of 35 to 40 degrees centigrade. But both James and myself, who were conducting this test, could start to smell burning, and we'd got no idea where it was coming from. So we did a quick pan round with the thermal camera, and the 2 meter by 1 meter by 1 meter resistive load bank that we were using was glowing there at over 200 degrees centigrade. So these 2 minute GaN FETs were sat there at 40, and this colossal bank of resistance was sat there at well over 200 degrees centigrade. That was quite an eye-opener into the benefits here that we're really focusing on. So once we'd established a set of design rules that allowed us to parallel GaN FETs and get the current sharing to be as good as it can be, we then applied that knowledge then into sort of a module design. And then once we had a module form factor, we looked at pulling that into the inverter design. So although Ricardo's done a huge number of inverter designs before, we really optimized the volume here around the dimensions of the GaN module. As a result of that, we've actually got the volume of this 50 kVA inverter down to 2 liters, which is and the weight is also around 2 kilograms. So it really is a very compact inverter.
Fantastic. So I think that sort of technology and the process that you've been through there, obviously Michael touched on the impacts that we're all feeling, and the fact that we're in a virtual environment is fantastic, that we can get so many people from around the world together. But we should really be sat face to face, and you'd be able to show us the testing that's coming along. And I think that's going to be very exciting when we start looking at how these perform in a real application. Great. And I think that this, whilst I think the group of us sat here on the call are based in the UK, this is a global opportunity. My view on this, Michael, I don't know if you've got a feeling for this, that this is globally applicable. This is not synonymous or specific to a single global location. And I think automotive is, whilst pushing the boundaries of technology, there's also many other things where this could also be applied to sort of stretch out that. And just before you answer that, can I just say, those of you joining the webinar, so we really want to make this as interactive as we can. If you can get your questions posted as well, that means that we can either answer them in some of the dialogue we're going to have here, or if we don't get them woven into the chat that we're having here around the virtual table, I should say, we will ask those towards the end. So, Michael, just on that global picture, have you got a view there?
Yeah, I mean, the response from around the world is relatively similar in terms of adoption. In that I think we're just getting there. I think the technology is becoming usable, and efficiency rates are getting to a point, and the battery technology is getting to a state that is, your next vehicle will be on all electric, or potentially even with a little bit of a range extender. What is interesting, though, globally, is that the driving factors between adoption are subtly different. In the US, the conversations are all around how does that compare to, the dollars per kilowatt? How does that compare to the dollars per, if the price for a U.S. gallon of petrol is less than $2. And when it becomes cost effective, they're going to buy electric vehicle. But the way they're selling those electric vehicles is they're just better cars. I mean, the technology within them are just better. They're nicer to drive. They are lovely vehicles. They, the interiors are fantastic. A lot of automated, a lot of gadgets, a lot of interconnectivity. In Europe.
Do you think the GaN will add to that, though, Michael, with the switching frequency capabilities of it? So some of the potential motor wine or any of that. From your conversations, do you see people buying into the higher switching speed capabilities?
In certain applications, and Dilder and the others on the application side will could have a strong view on that. But I think that just generally, electronics operate more efficiently when they switch higher. One of the things that Simon alluded to is slew rates, and we have to be aware that in the traction inverter we've got limitations because we're trying to drive these electric motors, and they themselves are very highly sensitive to higher frequencies. But I think just generally, it is a giant smartphone sitting on four wheels with a battery, an electric vehicle, and some controls, and potentially a few seats. So huge amount of semiconductor material going into these. I think if you think about the user experience in the U.S. compared to the more, you've got the green issues in European countries, and then you just got accessibility and petrol prices in places like China and and elsewhere in the world. But I think just across the board, where you think you can get 1 million miles now out of a vehicle, electric vehicle, which was not possible with an internal combustion engine, it's going to drive. All the other thing is, of course, depending on the country and the size and shape, 20-30% of total dependency for import of oil reserves is because of vehicles. So if nations can eliminate that dependence on imports of oil, like places like in China, then there is a huge incentive for them to get people to adopt the electric vehicle.
So the sort of green economic recovery that so many nations are now talking of is going to also help catalyze these electric vehicle growth.
All the stars are aligning.
Yeah. So I think maybe one with Dilder and James really here on the applications side. So we talked there about higher switching frequency being beneficial. What sort of frequencies are being used in the inverter that's being developed here? And the high DVDT is well known to cause motor winding issues. And how do you start to look and prevent high DVDT creating those problems for motors in future powertrains?
So with regards to the motor design, there's a few things you can adopt. So you can look at the motor windings. You can try and minimize the inductance, maximize the resistance of the motor, and also looking at the impregnation of the motor windings. So developing a machine for the inverter and accompanying the two is key. But this is something that can be done, and it will definitely have benefits with the higher switching frequencies, better efficiency, and as you've alluded to, with lower ringing or less noise that's audible. So there's many benefits of going to this type of switching frequency.
Dilder, are you seeing these sorts of things in wound components generally with GaN?
Yeah, it's one of the things is that with the IGBT or silicon-based solution, we never thought about that, okay, the motor is quite capable of handling whatever it offers. But suddenly the gallium nitride came in, it says, oh my God, it's so high DVDT. And the slowing down DVDT is possible, and that comes with the switching losses, right? So what happens now, the motor manufacturers are suddenly coming up with, right, how can we handle these higher DVDT and push the frequency up? So that's why there is a huge drive for the new motor manufacturing, electric motor manufacturing, that's been pretty not going as fast as it should have been. But now the silicon carbide and the gallium nitride, the wide band gap materials, suddenly started pushing these designers of the motors now coming up with the better and better motor windings so that it doesn't start causing all these bearing current, the inter winding currents and all these things. So yeah, so it's developing in parallel now. Now there is a huge drive to improve the motors as well. But we can slow it down, again, but that's not the purpose. So
no, please don't slow it down.
Exactly. It's like you have got a V8 engine or V12 engine, and then suddenly you want to slow it down.
I think you can think of it more. Sorry, Bill.
Go for it.
You can think of it more like all we've done is we've pushed technology now to the extent of where it is, and we've just discovered the next weakest link.
Exactly.
There's a fix out there. There's definitely a fix out there, and then as we push further forwards with this, we'll find the next weakest link.
Exactly.
It's development. It's the way life is.
Yeah, and we're continuously trying to improve that. Yeah.
Yeah, and I think that from all that as well, it seems to me that there's becoming a higher and higher drive on that system level thinking, rather than we design an inverter here, we get a motor here, we stick it to a transmission in the case of an EV here. That seems to be a thing of the past, really. And there's a lot of work then around how to bring that together, because obviously your motor design is going to be so dependent on your inverter or vice versa, and then your transmission and how it behaves.
And we're seeing that across the vehicle. So you normally have an onboard charger, then you've got this big DC-DC converter. You start thinking, well, let's put them together. Now you have charger converters. As you started lowering the components, lessening the weight, integrating other components, can you use the traction inverter as an onboard charger in some instances? So all of these ways to improve the efficiency and just the vehicle for the end user are all being considered now.
And you talked earlier, Michael, sort of about growing this from the 50 kilowatt into larger power ratings in the same package. And yes. I'm sure that some of the people who are listening here will have been on earlier webinars, but I think it's worth just touching on that future roadmap of these GaN devices, because no technology stays still, and one that's as new to the market, it's fascinating that before we've sort of got full adoption, the next generation is being looked at and grown and delivered.
Yeah, I think more than being looked at, of course. As you can imagine, Nexperia, a sensible size semiconductor company where nearly 50% of revenues are in automotive. Automotive qualification and quality and reliability is absolutely key to everything we do. AEC Q101, we managed TS 16949. So the next, we did this on a fully qualified process just because we're conservative that way, and we wanted to make sure industry was comfortable with that. The next two generations, we've just announced the release of the H2 platform. That would, it's basically a nice shrink, but probably about half the size for the same power outage we could get out of the same die size to go into these modules. And then we already have in test our H3 process that we expect to come out and be qualified for next year, again, fully automotive qualified. So I think the base components are there, and they will be qualified for these. Will allow Ricardo to do the testing on this traction inverter, and then as we build up and as we get demand and as we get interest for an 85 kilowatt drive system or potentially 120 kilowatt drive system for a real vehicle, I think we'll be in a very strong position to be able to provide both the device, but even some almost nearly reference design capability, which I think is going to be the interesting part of the discussion. I think Dilder runs the roadmap, and so I think you've seen some of the results for H3 now.
I'm just giving you one of our sub 18 million device, and managed to achieve in excess of 98.5% at 12 kilowatt, just using one device, one high side and one low side device. We managed to get in excess of 98.5%, and in about 8 kilowatt is more than 99%. So it's a huge, and which we can see and feel like what the GaN can offer.
So it comes back a little bit there, Dilder, to some of Simon's comments earlier, that actually as we drive these efficiencies up, how do you measure those? We're now into percentage points of loss rather than, or 95, 96, 97. We're now 99 point something. That's a fantastic place to be.
Yeah, the one interesting part of that one, say for example, if we are comparing something is about 92 or 94% efficient and moving to 99% efficient, it may sound not a big deal, apparently, oh, you are increasing by about 4 or 5%. But we are talking about a 100 kilowatt system. When you have got 99%, you are only 1 kilowatt of heat you need to deal with compared to about 7, 8 kilowatt of heat that you'll have to deal with. Is suddenly that actually drives your battery capability down, your mileage goes down. So there an extra heat now you'll have to cool with your battery power. So it's a huge benefit going into the power GaN.
And so in terms of that then, so there's clearly some benefits you're talking about there, but are you seeing already adopters of GaN within the OEM environment within automotive? Or Michael, you touched on some of how driving these to failure and really getting to that level and that being a real important thing to you here. Where are the OEMs in terms of their adoption?
Well, we know that there are still a lot of IGBT systems out there, even though, as I suggested, when we were one of the first to provide IGBTs almost 20 years ago, it's a solid solution, not particularly efficient, but everybody understands it and recognizes it. You've got a lot of silicon carbide solutions out there, been around a little bit longer, and GaN is next. So where are they in the adoption? We're still not yet at 2 million vehicles a year. So we're in that, who's going to put this into the first mass-produced car? Is that going to be, who that's going to be? We can name all the OEMs who are looking at it and driving development. So I think it's in process, but nobody's driving around with a car today that's got a GaN traction inverter inside of it. We're not there yet, but we do expect it to happen. Certainly, probably 4 or 5 years ahead of when we start to get to peaking at 2030.
And I think that if they were, then to be honest, the webinar would be a far less exciting and interesting one. So let's be thankful for that at least. Whilst the technology might not be out there, we've got a fantastic opportunity to talk about it now.
And just to compliment with Michael, we started seeing the adoption in the industrial market and in the power supplies and others, because this is the natural trend of the new technology. It comes into the industrial first, where is the less risk, and then slowly it gets into. But one thing we haven't seen anybody doubting is the GaN offers better efficiency and better performance than even silicon carbide. So this is more or less well accepted norm currently we see in the OEMs. They see that the GaN has got something more to offer.
And again, the cascode connected GaN is so easy to drive. It just looks like a standard silicon MOSFET from a gate point of view.
Yeah, absolutely. Yeah.
So I think that we on the driving then, Simon, sort of there and how you drive devices, and certainly from my days driving silicon devices in particular and things, how you drive really does drive sort of EMC.
Yes.
Performance. So, and I know that we've touched on the fact that COVID has impacted testing things. Have you got any view or feel for the EMC yet, or any things that are considered in the design to try and ensure that it's
sure? I mean,
good?
Again, to sort of increase the overall efficiency, what we've been very careful to design for and to minimize is ringing in any part of the drive. Whether that's on the gate or whether that is or gate source or whether that's across the drain source. So really, we've really tackled that. Obviously, we do have a very high dV by dt on the devices, and we've spent a lot of time looking at that to try to ensure that we were employing best design practices around there. Obviously, we haven't got any EMC test results to show us yet, but the testing that we've shown shows that we don't have ringing. We do not have any ringing on the inverter. Obviously, EMC isn't just about ringing, but that was going to be the primary obvious source. Moving forwards, if it was shown to be a very large issue across many applications, I don't see why you couldn't essentially drive the gate with a shaped drive voltage, current, power to effectively ramp up and then tail off. So you're controlling the dV by dt at the extremities of the drive.
Just to add to Simon, we have done some EMC testing, EMI, and our device. One of the big advantage of GaN is that it doesn't have any QRR. So when you have got that kind of the overshoot, doesn't bring excess noise and trouble with it. And obviously for the EMC or EMI, you need a transmitter for carrying that DVDT into the problem area. So what we do, usually we decouple the DVDT from the transmitting of that DVDT. So that eliminates that one. So from the device point of view, it may have got a very high DVDT, but it actually doesn't overshoot as much as the silicon usually does because of their QRR.
Yeah, correct. Yeah.
So it's sort of almost an inherent benefit of a gallium nitride solution.
Yeah, it is.
Of a cascode specifically, yeah.
Yes. And cascode specifically, obviously, our gate rating is plus minus 20 volt, very robust, and you don't need to worry about the gate falling apart.
Yeah. Always useful, I would say, when trying to get a reliable solution.
Yeah, and this cascode has got a very beautiful freewheeling diode, so that carries...
An Nexperia one by any chance, Dilda?
Huh?
An Nexperia freewheeling diode by any chance, is it?
Yeah.
Yes. Designed by Dilda.
And automotive qualified as well.
Excellent. One other thing that this sort of seems to be boiling down to, and I don't know, Michael, if you've got a view, is this sort of technology and the growth of electric vehicles changing the position of tier ones in the market, and are OEMs trying to become owners of their own technology, or are you still seeing as much engagement with your tier one market as you were historically?
Yeah, even more so. You know, you can imagine the OEMs in these kinds of technology transitions. And again, I've experienced it in lighting, for instance, where the two largest lighting companies, GE and Philips, had to exit out of lighting because they just couldn't deal with the technology transition to solid state lighting. In the OEMs, just think about all the way from the supply chain, the WIP, their suppliers, their factories, the developments that go into engines, internal combustion engines, and then all the way through their supply chains, distribution, regulatory issues, charging points, the whole infrastructure and support, maintenance, recalls is completely new, completely different. You know, Volkswagen announced 88 billion euros to support the transition to battery electric vehicles. This is a massive transition. And then people will, you know, you get into conversations with people not in the industry will say, well, what's the difference? Instead of an internal combustion, I've got a big battery now driving the car. And I think the transition is going to be is quite significant. When you can buy an electric vehicle on Amazon and have it delivered that way, and there's no dealership available, it's all online, and somebody comes to your house to fix something when it's broken down.
Computer on wheels.
That's just transitional. So I think that the tier ones, if you can imagine, then people like Amazon and delivery companies who are having to deliver packages in these zero emission city centers don't necessarily have to buy a Volkswagen or a GM product. They can buy a no branded delivery van, which we're seeing now with these kind of startup car companies. Royal Mail just announced their electric vehicle is going to be built by a company in the UK, not one of the large automotive OEMs. So that, but the OEMs still have to be supportive. So you don't want to be competing with your customer That's a challenge. The whole industry is in challenge, and the whole industry is in flux. It's going to be very, very interesting times these next 5 years. Fascinating.
Absolutely, because most of the OEM relish their engines, right? And their gearbox, and those are the two major items disappearing from their, how do you make yourself different from others? So that particular aspect suddenly disappears, and now you'll have to make the best electric motor with the best converter, then combining. That particular aspect is scary for the big OEM.
Yeah. And you touched there, Dilda, on gearboxes, and I just wonder if James or Simon, you've got a view in terms of we've obviously got now the ability to switch faster, which means we can accurately control much higher speed motors. That in itself is potentially going to give a impact on the transmission design, etc. Looking at that sort of system overview and the holistic system, have you got a view on the movement of that and how we can gain the benefits in motor size, etc., to give a system that's robust and reliable?
Yeah, so I think by moving to higher switching frequencies, so we're targeting 30 kilohertz at the moment. That enables you to run the motor faster because you can modulate the sine wave and keep a clean, smooth signal. And as you increase the speed to get the same power, the torque reduces, which drives the dimensions of the machine. So a faster running machine means that you can reduce your packaging size of the machine greatly. And going into an e-axle, this will reduce the packaging, and you can still stick with either a single ratio gearbox on the output. But it can affect the Vmax of the vehicle and allow you to operate over a faster speed range. So I think there's lots of benefits seen from the higher switching frequencies.
Yeah. And
it'd be fair to say that you can also reduce the size of the magnets as well in the motor. Obviously, they're going to be a fairly expensive component of a motor, so you're reducing that cost. You can integrate potentially that inverter now directly into your motor as well. So you're reducing your packaging, you're reducing the number of components that you have, and primarily you're also increasing reliability because you're reducing the number of connectors that you have within a vehicle.
Fantastic.
I think smaller, and it's getting smaller, lighter, right?
And ultimately, you can take that either, I suppose, as range, or you can reduce the size of your battery pack and have a cheaper overall battery.
Absolutely. Yeah.
So, another sort of quite a technical one on the inverter itself. Questions come in, so thank you for those. Keep the questions coming in. Inductance, the DC link capacitor, is often an issue in terms of the stability and reliability. Have you looked at that and considered that, and how's that sort of thing being approached?
Certainly has. So obviously we've got much higher switching frequency here. So what we have is a bulk film capacitor local to the DC terminals, and then distributed across the printed circuit, the power board we call, which is printed circuit board, that's got heavyweight copper tracking on it for your DC link. Local to each module, we have stacked ceramic capacitors arranged in a low loss configuration. So that really helps minimize the inductance very much.
And I think on you're talking there about getting things closer to the module and just sort of extrapolating that view with what Mike was talking about of the 150 kilowatt future. Would it be plausible to sort of take some of the research that I've seen coming out of universities where they're looking to integrate some of these passives within a module on the power stage? So they're looking at putting small power passives within modules as a route to, and that's certainly something that's being looked at.
That's actually what we have done on this project. So we needed the gate drivers really to be as close to the GaN FETs as we could get them. So we took the decision to integrate those into the power module. And also within the power module, we have some additional DC link capacitance there as well.
Okay, so that is something that's going out to the future. And I think that will then help, because I would anticipate you get to 100, 150 kilowatt, assuming the voltage is maintained, your current's either going to double or triple. Yeah, then you're going to need bus barring as opposed to a power planed PCB. So having localized would So fantastic. I think that that's been considered at this stage of your development. Yeah. And I'm going to ask the big question that's come in a couple of times now. What are the pros and cons of gallium nitride compared to silicon carbide? And I don't know who would like to. Still, did you want to start us off on that? Because you've talked about the very passionately about the benefits here of silicon gallium nitride.
Okay, let me start with Michael. You can jump in at any moment.
This is a path we've beaten down quite often. So
I'm sure it is. The question's come in a few times. I think it's important we address the elephant in the room.
Yes, exactly. One of the things is that we are talking about GaN on silicon, which made it possible that the GaN price is in the order where it is the people can afford it. Is one of the things is that when the GaN on silicon came in, and one of the benefit of GaN on silicon is you can use any silicon-based fabs to process these devices. The design that we do, and we can process it with the silicon-based infrastructure. It's all the tool set. You don't need to make a major modification. And also, as you know, that the silicon ingot come in a huge size, right? You have got the 8-inch, 12-inch. So you can get a huge ingot, which is in excess of 2 meters long, and you can get thousands and thousands of wafers. So the silicon price is very cheap. On the other hand, the silicon carbide, it doesn't grow like the ingots that you get in the gallium nitride. It comes with a small crystal at a very high temperature processing to get only about 30, 40 or hundreds of wafers from one block, and which makes the starting material pretty expensive. That's number one. And number two, in the processing in the fab, you need a dedicated fab with a completely different set of tool set, and also the temperature for your drive-in diffusion and ion implantation. These are in excess of double, and in some cases triple. So you'll have to have a higher energy, completely different set of processing equipment, and the processing time required. So fundamentally, silicon carbide is more expensive, that's for sure. And GaN has the potential, as this wafer size goes up, it has a potential to come down to very close to silicon pricing in that sense, although the epi is expensive, but it will never be as expensive as the silicon carbide fundamentally. And from the die size point of view, obviously silicon carbide and gallium nitride both has got a potential to get a very low RDS(on) for a small die. And that's where obviously the silicon carbide can beat in some aspects, but overall it gets beaten because silicon carbide is vertical, but the gallium nitride is lateral. That's why it has got a bit of limitation. But end of the day, you cannot make it too small when your total power loss is concentrated in a very small area. So then you'll have to make it bigger. So the compromise, I think that's why the gallium nitride is very well positioned.
Okay.
It's wider band gap as well, right? Fundamentally, GaN is going to be able to operate much higher frequencies and just better efficiencies. It's always going to be just slightly ahead of silicon carbide. I think the other big advantage silicon carbide has, which is why we, when it originally came out, one of the advantages silicon carbide was its thermal performance. It's still, its thermal conductivity is pretty close to pure carbon, right? So you can operate at very high temperatures.
And I think that it's often a discussion that's had around on those devices and things. So I think thank you for that sort of fairly simple to understand explanation as well, Dilda. So appreciate that. And someone's come back on some of the sort of discussion around sort of power modules, and I think that that's a really interesting area that's being developed. How GaN power modules and getting that, and obviously there are silicon power modules out there that have got integrated parts within them. How far do you believe people want to go on that in terms of integrating intelligence within power modules? Obviously the the positive side of that is you end up with a power module that you can plug and play almost, that has a lot of protection around it and is highly robust. The downside of that, from the purist engineer in me, is I don't get to control very much of how it performs and what it does. I just wonder if you've got a view of sort of a roadmap on what people want in the integrated power module space.
Yeah, what people want. I mean, Nexperia is a discrete supplier, right? So we supply discrete devices. The roadmap that we have for gallium nitride includes, two types of packages: through hole and surface mount, and then die. And the die primarily is aimed at module manufacturers. And we are working with a number of the large global power module manufacturers who understand those end markets and what the end markets are looking for in terms of integration of drivers and controls. There was a move, having been in power for 25 or 30 years now, it kind of goes back and forth between fully integrated power modules to all the way back to discretes. The issue on the fully integrated ones is if you have one failure, one small failure of anything within the integrated module, you got to throw the whole thing in the bin, and you got to replace it with quite an expensive module. The plus side is, as you said, you take it, you put it on your board, you mount it, you thermally mount it properly, and you're off and running, and you start driving. So simplicity in terms of assembly is key. And then you're just on a failure rate. What kind of failures? It seems to me, and the experience came out of the motor drives and even going into medium voltage drives, was that as the industry matured and became more comfortable with the technology, the more integration they were happy with. So we, e-drives now, the whole integrated drive motor electronics probably come with a fairly simple, either full bridge, maybe a series of half bridges like we did with Ricardo in this module, or just maybe discretes as they're with duals or quads. But eventually, as they get more comfortable, I think that roadmap will become further integrated, as with every other. And in the automotive industry follows the same. We're seeing more and more integrated modules in across our MOSFET applications.
Okay, and
including driver on board and that kind of thing. DR MOS, Dr. MOS.
Okay, and you touched there, sort of, Michael, on medium voltage industrial drives and that sort of thing. There's obviously an uptake in some of the vehicle segments of 800 volt solutions. What's the panel's view on the 800 volt, its applicability, and certainly I would say midterm 24-25 time frame? Is that a big thing, or do you think the majority are still going to be sitting at 400 volts? The 800 volt is more a high end vision. I don't know who would like to.
Shall I start?
Yeah, that would be wonderful.
So my view is that 400 volts is here to stay, certainly for A, B, and C segment vehicles. I don't think there's any benefit in having 800 volts in that segment. However, for sports cars, for luxurious vehicles, I think there are benefits. And obviously, if your battery terminal voltage is high, your current's lower. If you've got lower current, you need smaller conductors. You've got less weight, you've got less cost. In that, obviously, your battery contactors, components, creepage and clearance going to be larger, therefore more volume, bit more expense. But I think 800 volts in that segment is probably where we are. And also light delivery vehicles, for example, as well, probably 800 volts.
Yeah, in general, if you look at the car market, it's 80 kilowatt up to 130 kilowatt is the predominantly dominates more than 80-90% of the total vehicle market. So then that around 5 to 10% probably will go for very high performance, and that's where you would start thinking about 800 volt. The soon you go to 800 volt, you'll have to have got now another challenge of the insulation, right? You'll have to look into 1.2 kV, 2 kV. So your housing goes down, but your insulation then become a bigger challenge. And also of this safety feature around 400 versus 800 is a significantly different matter altogether. So it's only in the high-end vehicle it will remain. I think the low-end vehicle, I think it will remain with 400 volt.
And I think you've touched there, Dilda, though, on something we keep coming back to in this conversation. Is one of the most exciting things I see at the moment in the engineering space is the excitement of, actually, I can't just fix my bit. This is a system. And I really think that of all the things, yes, Michael, you kicked us off with 4 different areas we're trying to almost sequentially do that are new to bring this out to where we're going. But actually, we need to also look at this from a new engineering perspective in terms of solutions. Extract ourselves from this, I'm going to make the best widget, whether it's a DC-DC converter or an inverter or a charger or whatever it may be, and look at this as a system to ensure that we get the best out of whatever technology we choose. And I think that change in engineering mindset is something that is here to stay and something for the future.
Yeah, absolutely.
So I'm very conscious that I've enjoyed this and lost track of time, and we are 50 minutes into our 45-minute session. I'm not going to apologize because I think that we've covered some phenomenally interesting things. But what I would like to do is sort of go, are there any bits that I wish Will had asked me on before we say goodbye to everyone? And if I just go around my screen, my virtual table, and we can wrap up. If anyone watching the webinar has got a last minute question of I really want to ask now, or I'm sure that everyone would say, please contact us after the webinar. So all will not be lost. But Dilda, is there anything you wanted to sort of touch on to wrap up today?
I don't know. I think obviously the biggest advantage of these, trying to bring electric vehicle and power GaN technology participate in significantly reducing the carbon dioxide emission, and that's obviously a huge benefit for the humanity. That's the aspects obviously drives us towards the electrification, and we'll continue to endeavor our efforts bringing it as quickly as we can to the market.
Fantastic. And next on my roundtable, James, is there?
I think, no, I'm just looking forward to the testing phase, seeing how much we can push the improvements on packaging with the increased switching frequencies. And yeah, it's going to be exciting testing ahead. Excellent.
And Simon?
Exactly what James said. I really want to get to the testing stage. I want to see that motor spinning on the dynamometer. I want to feel how cold the radiator is.
Excellent. Well, I will say I'm pleased that practical testing is the absolute forefront. I can tell you as a man who learned a lot deal when the first time I blew up a high power IGBT, it makes you realize you don't want to do it again. I'm not suggesting that's what you're going to be doing here, but the practical element is of absolute importance. And finally, Michael, I'd like to first of all thank you and Nexperia for inviting me to be part of something that I've learned so much in the last 55 minutes on what you're doing. I think it's exciting where we are pushing the boundaries of technology, but give you the opportunity to sort of finish with anything else you want to add before I close out the webinar.
Yeah, no, I think we covered all the things that we wanted to cover, but I wanted to thank you, Will, for hosting the event. You know, you now as the leader of this driving the electric revolution in the UK, a fantastic organization, pushing all the right buttons. You know, we're a global enterprise, but headquartered in the UK, so we just love the fact that there is this kind of enthusiasm that we can find within country. And again, thank you very much for hosting the event. And I just want to thank everybody that joined today. And hopefully it was some benefit, and we look forward to hearing from everybody on our particular adventure.
Excellent. Well, thank you all. Thank you, Simon and James at Ricardo, Dilda as well at Nexperia. I've had a really enjoyable afternoon. Well worth it. The sun is shining here in Hertfordshire, so I am looking forward to getting out this afternoon. I will wrap up by saying I hope everyone keeps safe and well at this time when there is a lot of uncertainty around. Keep yourself safe, keep everyone around you safe. Thank you for joining us here today. I hope you've enjoyed it as much as I have. Thank you.
Thank you very much, all. Thank you.
Thanks, Will.
Super. Thank you, Will. Thank you, everyone. Please do not apologise for running over with time. It was more than worth it. A really interesting session. Really good to hear the thoughts and insights of the whole panel. So thank you very much.
Thank you,
So
Kelly.
that brings us to the end of this particular live session, but also concludes our live schedule both here on the GaN channel and also for day one of this event. So thank you very much to all our resident power experts. Thank you to everybody who contributed throughout the day with questions, and a special thank you to Simon and James at Ricardo, and of course our panel moderator this afternoon, Will Drury.
Thank you.
Our event continues tomorrow morning over on our automotive channel. So we'll start discussions on design insights. We'll start talking about technologies for 48-volt hybrid. And we also have a special discussion scheduled on our new silicon germanium rectifiers. So you can take a look at the schedule over on the automotive channel now. I wish you a pleasant rest of your day and look forward to welcoming you back to the Nexperia Power Live event tomorrow. Thank you.